In this video, we're going to learn how to graph reflections of functions, and we'll take a look at some mixed transformations. To identify if a graph is being reflected, you look for a negative sign. If the negative sign is outside of the function or not grouped with the x, it's a vertical reflection across the x-axis, or if it is grouped with the x, it's a horizontal reflection, which flips it across the y-axis. Again, in this video, we're going to take a look at using the parent functions to graph our transformations. Our first transformation is an absolute value function, and we have that negative sign outside of the function. It is not grouped with the x. So to verbally describe the transformation, we would say it is a vertical reflection. The critical point of the parent function is 0, 0. If you reflect 0, 0 vertically, it will remain at 0, 0. Domain and range, again, we'll get from our graph. Taking a look at our chart, our parent function we identified as the absolute value of x. So we'll take the absolute value of all of these x values we have in our t-chart. Because that negative sign is not grouped with the x, there is nothing grouped with the x, our x value is being left alone, and our y value is being multiplied by a negative. Keeping all of those x values from the first column, and multiplying all of those p of x values, those y values or outputs, by -1. Plotting those values, we had -2, -2, -1, -1, 0, 0, 1, -1, and 2, -2. Remember, the absolute value is a v, so make sure there is a sharp point at 0, 0, or your critical point if you end up shifting it. Domain and range. Domain is all real numbers because you can substitute any value into an absolute value. You can also think about sliding that vertical line across the graph. For the range, in this case, our graph is upside down. Typically, the range of the absolute value function is greater than or equal to 0, but when we reflected this vertically, it flipped across the x-axis, and all of our y values are less than or equal to 0. Now we're going to take a look at combining different transformations together. Taking a look at our first equation, we have a multiplication by 1/4 on the outside. It is not grouped with the x, so that is a vertical compression. Inside, grouped with the x, we have a -5. It looks like it's a shift to the left, so it's actually a shift to the right. As we've seen, the critical point does not change under stretches or compressions, nor does it change under reflections. The only thing that changes our critical points are shifts. In this case, our shift was right 5, so our x value will change to 5 and our y value will remain 0. Our parent function, notice we have after the parentheses the cube, so that is our parent, the x cubed. Cubing all of our x values here, and then figuring out how we're changing our x values and y values. Our x value was changed by adding 5. We shifted it to the right. And our y value was changed under a compression. We're multiplying it by 1/4. Adding 5 to all of those x values. And multiplying all of our y values by 1/4. Then we will plot those two purple columns for our transformed function. Because not all of my points will fit if I count each of these as 1, I'm going to count each of these darker bars as 2. My first point was 3, -2. Then we had 4, 1/4, 5, 0, 6 1/4, and 7 2. This was the cubic function. I know my critical point was 5 0, so I will have that curve around 5 0 on my graph. Domain and range. If the domain and range of your parent function are all real numbers, no type of transformation can change that. For our cubic, that is the case. Next, we have a step function, and we have a lot going on this one. Outside, we have a vertical stretch. Inside, we have multiplication by a negative. That is a horizontal reflection. And we are shifting it right 3. And finally, down 2. Domain and range we'll come back to. For the step function, it's challenging to do a t-chart, so I will show you how to graph using all of those transformations at the same time. We are missing the spot for the critical point, so let's get that added in. The critical point for the parent function is 0 0. The only thing that will change the critical point for a transformation is shifts. In our case, we are shifting it right 3 and down 2, so that will be our new starting point for our transformed function. Because it's easier to see for the step function, if I count each of these as 1, I'm going to do that. So over 3, down 2 is my new starting point. The vertical stretch does not affect the length of the bar. The length of the bar is horizontal. If we had a horizontal stretch for our step function, the bar would either grow or shrink if we had a horizontal compression. Since we do not have that, each of our bars will remain 1 unit long. We do, however, have a horizontal reflection. So instead of heading off to the right to make my bar, I will head to the left. The vertical stretch comes into play with the space between each bar. In our case, we have a vertical stretch of 2. So instead of going up 1 to get my next bar, I'm going to go up 2. And remember, with the horizontal reflection, I'm going to go off to the left instead of off to the right to make my next bar. So I'm going to jump 2 to make my solid point, head to the left for my open point, jump 2 again for that vertical stretch, head to the left for a horizontal reflection, and indicate that this will continue. We can also go in the other direction, vertical stretch of 2. This time I will start with an open circle because my closed circle is off to the right, and indicating the pattern will continue. Domain and range on this one. For our step function, our rounding down function, you can round any numbers, so our domain will remain all real numbers. For the parent function, the range is integers. However, on this one, with that jumping of 2, that's no longer the case. We don't get every integer as an output. So let's take a look at what integers we do get out of the function. Starting here, we have an output of 0. And then it jumped to an output of 2 and an output of 4. Below that, we had outputs of -2 and -4. Notice these are even numbers, so our range is even integers. And our last graph, verbal description, we have a negative that is not grouped with the x, so that is a vertical reflection. We have a 2 grouped with the x, so that is a horizontal compression. Remember, when it's grouped with the x, it's not normal. So even though it looks like a stretch, it's actually a compression. And not grouped with the x, we have a shift, so that is a vertical shift up 3. Our critical point for this function, it's our reciprocal function. The parent is 1 over x. The critical point is where those asymptotes meet. For ours, we have no horizontal shift, so that will remain 0, and we went up 3. Subbing in our values, 1 over -2, 1 over -1. This will be our asymptote because 1 over 0 is undefined, 1 over 1, and 1 over 2. Thinking about our transformations, what did we do to the x? The only thing that is horizontal is that compression. So we're multiplying all of our x values by the reciprocal of the 2, which is 1/2. For our vertical, we have 2 changes. We have a vertical reflection, so we'll multiply our y values by a negative, as well as a vertical shift, so we will add 3 as well. Taking all of those x values and multiplying by 1/2. And then taking those y values, order of operations, we'll multiply it by a negative, and then we'll add 3. So our -1/2 becomes +1/2 plus 3. -1 becomes +1 plus 3. We'll still have our asymptote along this line. 1 becomes negative plus 3. And finally, 1/2 becomes negative plus 3. Plotting those asymptotes to meet at my critical point 0, 3. And then we will plot the points from our second 2 columns. Starting at -1, 3.5, -1/2, +4. On the other side, we had 1/2, 2, and 1, 2.5. Remembering what the parent function looked like and using those asymptotes, we have 2 curves that go between those asymptotes. As a reminder, the parent function would have been in the other quadrants, kind of the first and third quadrants surrounding those asymptotes. So we can see our vertical reflection on this one because the quadrants that we're graphing in changed. Finally, taking a look at our domain and range. Domain, thinking about sliding a vertical line all along the graph. The only place where the graph is not defined is when x equals 0. You can also think about the domain on this one by looking at the denominator of our equation. Remember, anything in a denominator cannot equal 0. So that's where we get our x cannot equal 0 from. And finally, our range, thinking about sliding a horizontal line along our graph. The only place it would not touch is along that asymptote as well, which was at y equals 3. And no U-tries on this one again.